Yes. So there are different ways to represent these organic molecules, and we have already seen how to represent them in 2D, that is in dash form, right? So in dash form, we suppose we have to show molecule ethene. So ethene will be shown like this.
Are
See,
you not sharing your screen?
okay.
Thank you.
Now it is visible, right? You are able to see the screen now? Okay, so this is called dash form, in which we show the bonds by straight lines and we also show the atoms, right? For example, here ethene will be shown like this. This is called dash form. Next, we have condensed form. In condensed form, we omit the bond between carbon and hydrogen. So we don't show the bonds between carbon and hydrogen. So this, suppose we have an ethene molecule. Ethene molecule will be shown like this: CH2 double bond CH2. So that is ethene molecule. Next is called bond line. So in this, we omit both carbon as well as hydrogen. We don't show carbon as well as hydrogen. So the same thing can be represented as these two double lines. So that means there is carbon here, and because carbon has these two bonds, so there will be two hydrogens left. And if it is not any other atom, that means it is the bonds are, or the valency is being satisfied by hydrogen. So this is when you have molecules in your 2D, right? So this becomes easy. This is easy for 2D. So even the ethene molecule can be shown in the dash form like this. So this is the same ethene molecule which we have tried to show here in dash form, then condensed form, and this is the bond line form. Now let's see what will happen if we have to show it in 3D. So in 3D we have different you can say ways of showing this. The first one is called flying wedge or wedge dash form. Flying wedge or wedge and dash form, right? So what exactly is this? In this form, we know that, and this will be showing for 3D, and we know that 3D is when carbon has four different bonds, that is all sp3 hybridized. So in that case, it is a 3D molecule. So this 3D molecule, if we want to show, we show such that the central atom carbon is in the center, in the plane. So this carbon plus two atoms will be shown to be in the plane, right? And two more atoms which are left, they will be shown above and below the plane. So that's how this structure, suppose this is carbon, right? There is this. So what do we have here is, there are these two, suppose these two are in the plane, and this is in the back, and this is on the top or front. So like this, we try to show these different atoms, right? So now this is, again, we have to write here, like which is in the top, which is on the top, or which is in the back, or what all are there in the plane. So there should be a particular way or a specific way of representing them. So that is one of the ways is this flying wedge notation. So what we do here is we show these atoms, or sorry, these you can say linkages, like this. Right. So what you are showing here, what you are seeing here are this central, this is the central, the junction is the central carbon atom which is in the plane, and the straight lines which are there, they are also in the plane. So these two are in the plane. So the ones which you are shown here by green, they are actually in the plane, right? Then the atom, say this one, which is connected here by this solid or straight, this is called wedge. So this will be this is on the top or in the front, right? And what is left now, the atom which is shown by these, or which is connected by these uh, dashed lines, so that's why it is called wedge and dash form. So the atom which is connected by dashes, that particular atom will be called, or that will be actually representing the one in the back, right? So this is the way to represent these 3D molecules, right? There will be three in the plane. Out of three, one is the central carbon atom, and then you have two substitutes in the plane, which will be shown by straight lines, solid lines. Then there will be one on the top of the plane that will be shown by this wedges, solid wedges, and the one which is on the back of the plane, right, that will be shown by these dashed lines, right? So such linkages will be shown like this. So in order to understand this, let us consider one molecule or see an example. Say for example, we have this lactic acid. This lactic acid is a compound having carbon, then COOH, and one more CH3, that is methyl group. So these are in one plane, and then there will be one OH that is on the top. So this means that is on the top, and then one at the back, and that one which is on at the back, that is actually your hydrogen. So hydrogen is at back, this OH is in front or on the top, and this COOH and CH3, they are in the same plane. Now this compound is called lactic acid. Same way, next compound is, say, tartaric acid, and these compounds you will find again its use, or it will be repeated again when you will study acids, and even when you will be studying the biochemistry, even in those chapters you will find this. So next is tartaric acid. So this tartaric acid is nothing but, you can say, two lactic acid groups combined together. In place of CH3, there will be another group having the same thing. So it actually looks like this. You have group like this. Right. So this means what? This carbon and this carbon, they are in the same plane. And then you have this group which is in the same plane, and that group is, suppose this group, this is COOH. So this is also COOH, right? So they are in the same plane. And then in the same plane, so if you see this particular carbon, it has two substitutes. One substitute is this COH and another substitute is this carbon. So these two are in the same plane. So total there are three in the same plane. And then you have one which is on the top. So the one which is on the top in this case is OH, and here also OH. And then there is one left, and that one which is left is actually your hydrogen. So that if we want to show, we show it like this. So this is your hydrogen. So now we don't need to draw it with so much care here. As you can see here, we can directly draw these with the lines. Dashed line means it is at the back, and if it is solid wedge, it is on the top, and if it is solid lines, just lines, that means it is actually in the same plane. So that's how we represent. And as you can see here, it is little difficult to draw such structures, but this gives a very clear idea about the orientation of the substituents or the groups which are attached to the carbon atom. So these are the two examples, that is lactic acid and tartaric acid. Now the second form or the second representation is called the Fischer representation. So let's see what is that Fischer representation. Now in this Fischer representation, this is something which will be mostly used in optical isomers. OI means optical isomerism. So it's again very simple. We are not going to draw these oblique lines or dashes and wedges as we have seen in the previous example or previous representation. What we are going to do here is we are going to draw just vertical lines and horizontal lines. So the vertical lines, that is the lines like this, and the molecules or the groups or the atoms which are represented on these vertical lines, they actually represent those groups which are on the back of your screen or of the paper, right? And then there will be horizontal line. The horizontal line, if there is something on the horizontal line, that actually means they are on the front or on the top of the screen. So these are the only two things here. That is, vertical means back and horizontal means front, right? So for example of this, as let's see, we have this COOH. So now in this case, you have actually the central carbon atom which is in the plane, right? In this case, there are two things we have seen: back, front, and then the central carbon atom, which will be, or you can say the point of intersection, that is in the plane, right? So this is point of intersection, and that means what? These are in the plane. Whatever atom is there, that is actually in the plane. So that means what? Suppose I'll represent a molecule like this, say same lactic acid. If I have to represent using Fischer representation, I'll represent it just like this. Now, if I want to show that COOH is behind or in the back of the screen. So I'll write it here, COOH, right? CH3. So these two are at the back. And then if I'm saying H and OH on the horizontal lines, that means I want to show, or this in this molecule, the H and OH group are actually on the top, right? So this actually means what? These things which are there. So this is on the top, and the one which and this one is in the plane, and these two, that is COH and CH3, they are in the back. So it is very easy to draw, but the only thing is here, only thing which we have to take care here is that we have to remember this notation, that horizontal means top and vertical means back, right? Another example for this can be this, say tartaric
But how
acid.
do we know that?
Yes,
How do we know that they're in the same plane?
they are not in same plane. Just there is only one. Only these point of intersection are in one plane,
Okay.
right? See what actually is this. This tetrahedral structure is actually like this, right? So if you see now, these three, you can say that they are in same plane. These three, right? I can put it on one plane. So the 3 points will be always coplanar, right? 3 points may or may not be collinear, but if you have 3 points, with 3 points, you can always draw a plane. Up 3 points will always be coplanar. So these three can be coplanar. Even these three can be coplanar. So it's not like if they are in same plane or not. We are here to represent the 3D. So what we are showing here is that in this representation, we are taking 2 in the front and 2 in the back. If you see the previous one, we have taken 3 in the plane, 1 at the back, and 1 in front of the screen, right? So that was that
So we
representation.
can choose the element. We can choose the element according to our choice. Like
No,
where to place it.
no. This is one of the possible arrangements, right? And there can be multiple such possible arrangements. It
Okay.
is nothing but rotation. If you rotate the molecule, something else will happen. We'll see the rotation as well. So only thing is, it's not like always you change your location, you change your point of view, you will see that the one which was, say for example, right now you are seeing it from the front of the screen, right? Now you
Yeah.
assume yourself to be on the left side or right side of your screen. Now you cannot say that H and OH are on the top, because if you see from the side, left hand side, H is on top and OH is at the back,
Yeah.
right? So this thing that what is the orientation of this, that also depends on from where you are observing it, right? Your
Oswald's
point.
perspective.
Yes, so that is important, and we have just simplified that to a configuration where we'll be showing 2 at the back and 2 at the front and 1 in the plane. So that representation is called Fisher representation, in which the groups which are at the back will be shown on vertical line, and the groups which are in the front, that will be shown on the horizontal line. Right. So it is easy to draw, but as you are also right now facing little difficulty in visualizing this. So that is the only problem with this. But the thing is, because we have only two things, horizontal means back, horizontal means top, and vertical means back. So by practice, you will come to understand this easily. Right? So this is this Fisher representation. Okay, so next let's see some other compounds, and these are the compounds, or these are the molecules which you will, this representation you will find its usage mostly in the biochemistry chapter, right? Some other examples of this, say for example, yeah, tartaric acid here. So this tartaric acid, as we have seen, tartaric acid was shown like this, right? So there are actually two junctions, right, where there is, so these junctions represent carbon. So this is a carbon, this is a carbon, and they are in the same plane. And then again, whatever is on the top, whatever you want to show on the top, you will be shown on the horizontal line, and whatever you want to show on the back, that will be shown on the vertical line. So suppose we show COOH and COOH here, that means we want to say that COOH is at the back. So if I draw this, yeah, it will be like this. And then what do we have? We have H and OH. So this H is here, OH is here, or H here and OH here. So they are on the top, right? This is tartaric acid. And if you see this, H and H are on the same side, OH and OH are on the same side. This is called cis form. And if they change their side, that is called transform. So this was your tartaric acid. Let's see one more molecule, again very important molecule, that is glucose. So these molecules or structures which I am showing right now, they are very important. Try to learn them and practice them. Now in glucose, you have 4 such junctions, right? And here it is an aldehyde, so that group, and here there is a alcohol group, right? And then you have just H, OH, H, OH, H, OH, and H, OH. Right? So glucose are nothing but multi-hydroxy aldehydes. There are multiple hydroxy groups there, and it is an aldehyde. So that's what glucose is, and this is the example of, or the structure of, glucose. So what do we see here? How many OH are in the back?
No H.
This one.
Oh, that's also, yeah, sorry.
Right? Okay, so that is your Fisher representation, which we will be using when we will be discussing the optical isomers. Next structure in 3D is called Neumann's projection.
Yeah.
And this is very simple. This will be used to represent mostly the conformational isomerism. So conformational isomerism, if you remember, this is a fake isomerism where the molecules like which we have seen above, right, like this tartaric acid. So this tartaric acid, in this, the carbon-carbon bond, the main carbon-carbon bond is actually a single bond, and due to that single bond, there is zero restriction. So this can rotate, and it can rotate and form a staggered form and a eclipsed form. So staggered form, eclipsed form means when same groups are eclipsed by the front, the back groups are being eclipsed or being covered by the front group, that is called eclipsed version. And so that will be the front one will be shown by dot, the front carbon shown by dot, the back carbon will be shown by this circle, and then these groups. So this means these groups are attached to the front carbon. So the green ones are attached to the front carbon. And if I have to show the eclipsed version, what I show here is this, that they are just behind this. They are actually totally eclipsed, so you won't be able to see them, but we have to show them to make you understand that there are three in the back as well. So that's what we are showing here. This form is called eclipsed form, right? And there is another version of this that is called staggered form. In staggered form, if front is like this, back will be here. So if you see from the front, all of them, all six will be visible. This is called staggered form. And obviously, if I ask you which one is more stable, which one is less stable,
Staggered.
so yeah, staggered is stable and this is less stable, right? And the same thing can also be represented by a fourth notation or fourth form that is called sawhorse form. So in this form, what we do is that same stagger, the eclipsed, the Newman's projection, you can see that now instead of seeing it from the front, you are seeing it from an angle, from an oblique or from a side. So suppose you move to the, you can say corner of your screen, and from there, if you are seeing it, then how it will look like. So it will look like this, which we have already seen actually earlier. So it may be like this, and the eclipsed form will actually look like this. So this is again eclipsed form. And the same the sawhorse form for this will be the front is like this and the back one is like this. So this is again staggered form, but this staggered and eclipsed are in fourth notation that is called sawhorse form. So these are the four different representations of four different representations of 3D molecules or molecules in 3D. Out of these, I think the conformational isomerism we are not going to study more in detail. This is all we have in conformational isomerism, that it will have a carbon-carbon single bond, and if it is able to rotate here, because of this single bond, it will be able to rotate here. So one form can change from eclipsed, can change to staggered, from staggered it can change to eclipsed. So it has two rotations or two orientations. So those are two different forms, but they don't exist in reality. And because they don't exist in reality, so that's why they won't exist in reality. I mean, they exist in reality, but they don't remain in the same form forever. Whatever structures we have seen earlier and even the orientations, those structures or those orientations are forever, right? Such molecules have two different versions at the same time, but here same molecule changes its version or orientation. So that's why these are two different forms, but we are studying it in isomerism, yet we won't call it real isomers. We say that it is fake isomers or unreal isomers, right? So this was about you can say the structures or different ways to show these structures. Okay, so I think the session will end now. So before ending that,